So this is the fourth lecture on continuity. In the last class, we finished off with the sequential criteria of continuity and the proof of that. As soon as we have the sequential criteria of continuity, as we did in limits, we have the same algebra for continuous functions over here as well. That if f and g are two continuous functions defined over a domain D and continuous at a particular point, let's say C, then the functions f plus g, f minus g, f times g, and f over g, provided of course gc not equal to 0, are all continuous at C. Now the proofs of this thing are very much in the same way, exact same way as we did for limits, algebra of limits of functions, and these things are guaranteed by the sequential criteria. We have one sequence xn converging to C, then fxn will converge to fc, gxn will converge to gc since they are continuous at that point. So their sum fxn plus gxn will converge to fx plus fc plus gc. Fxn minus gxn will converge to fc minus gc. If fxn into gxn will converge to fc into gc. If xn over gxn will converge to fc over gc, and so on. So by sequential criteria, this thing is a one-liner proof, and we have seen this in case of limits, and that is the same thing is true in case of continuity as well. Okay, so this is just a theorem because of its importance, but this is actually a mere corollary. All right, so after these two things, we will see a few more examples. These examples are important. A polynomial function is always continuous. Okay, so we know a polynomial function looks like this, that a coefficient times x to the power n, a coefficient times x to the power n minus 1 plus a coefficient times x to the power n minus 2, and goes on like this, goes on till xth term, and there is a constant term at the last. So these are all real numbers. So a naught x to the power n plus a1 x to the power n minus 1, and so on. This is a polynomial. Since both the constant function and the identity function are continuous, the constant function is continuous. K is fx equals to k is always continuous. We have seen in the last class, and the identity function x maps to x. This is also continuous. Now over here, let's say a naught x to the power n. This one is nothing but x into x into x. This way it goes on n times. This x is a continuous function, this x is a continuous function, this x is a continuous function. So the product of all of them will be a continuous function by this result, by this result, algebra of continuous functions. So if x to the power n is a continuous function by repeated application of this one. Fine. A naught x fx equals to a naught is a continuous function. That is a constant function, hence continuous. So a naught into x to the power n will again be a continuous function. There is nothing special about a naught x to the power n. A1 x to the power n minus 1 will again be continuous by the same argument. A2 x to the power n minus 2 will be continuous by the same argument. An minus 1 times x will be continuous by the same argument. An is by default continuous constant function. So all of these terms are continuous functions. So their sum will be continuous as well by again applying this theorem. Okay, so we just need these two facts, that the constant function is continuous and the identity function is continuous. Constant function fx equals to k, this is continuous, and the identity function, this one is continuous. So if we have these two, then by applying this theorem over and over again, we can guarantee that any polynomial function is continuous. Next one, this is an exercise for you. Mark it down. A is a fixed real number. The map x going to mod of x minus a is a continuous function. X maps to the distance of the point x from a. Suppose x equal to 1, then fx equals to x mod of x minus 1. X equals to 10, fx will be mod of x minus 10. So for any real value a, you need to show that the map fx equals to mod of x minus a is a continuous function. Okay, if you draw that graph, it will be very much intuitive for you, almost clear, and then you just need to write down the things formally. Next up, we have got this. Let f be a function defined by this Dirichlet function. Remember, fx equals to 1 at the rational points and 0 at the irrational points. Okay, it defined over the closed and boundary interval 0, 1. The Dirichlet function we already came across in the Riemann integration course. This function is discontinuous everywhere in 0, 1. Everywhere discontinuous. Nowhere, there is no point where this function is continuous. Okay, let's see. Let x be a rational point in 0, 1. So we will show that x is a rational point and there the function is discontinuous. Next, we will show that we will assume x is an irrational point and the function is discontinuous at that point too. Okay, so these are our two-stage proof. At the first stage, let x be a rational point. Then, by definition, if x will be 1, choose a sequence Pn of irrational points, since irrational points converge into x. Since we know that both the rational numbers and the irrational numbers are dense in 0, 1, that is why we, for every point in x in the interval 0, 1, we will have a sequence of irrational points Pn converging to x. Then f of Pn, this sequence, the functional value sequence, is the constant sequence 0, because Pn's are all irrational numbers and the functional value at all irrational points is 0. So then this one is a constant sequence 0 and hence converges to 0. Constant sequence converges to the same number, which is not same as fx, because fx equals to 1 since x is a rational point. Therefore, by sequential criteria, f is not continuous at any rational point x in 0, 1. The same will be the case for irrational points as well. So let x be an irrational point, then the functional value will be 0. Then applying the same technique as above, we can find a sequence of rational points converging to that irrational point x. So the functional value sequences will be the constant sequence 1 and the functional value will be 0. Hence the sequence that does not converge to that fx. So therefore by sequential criteria, f will be not continuous at the irrational points as well. Next up, this example is extremely important, extremely interesting as well. Now let's see what is happening here. F is such a function such that f is an additive function. F is an additive function. F of x plus y is equal to fx plus fy. Okay, you are provided that f is continuous only at the point 0. F is defined over entire R. F is continuous only at 0. Then show that fx looks like k times x. Okay, fx is nothing but a straight line. Fx equals to k times x. There exists a constant k such that for all x, fx equals to k times x. Let x be arbitrary. First, there are few steps. In the first step, we are going to show that this continuity at 0, this actually translates to continuity at any point via this condition, that this additive condition. Let x be arbitrary. Then, since 0 is a limit point of R, f is continuous at 0 implies by definition limit of f of h as h tends to 0 is equals to f0. Okay, this is the definition of continuity at a limit point of the domain. Therefore, limit of f of x plus h as h tends to 0, this is f of x plus h by this one is fx plus fh. And if fx does not have any h component, so this is a constant with respect to this limit h tends to 0, so this will remain fx, and fh will be 0. Limit of fh as h tends to 0 is 0 is f0. This is a mistake, sorry. So this will be f0 fx plus f0. I should have proved that f of 0 equal to 0 before. I have proved that, but this must come before this. So this will be fx plus, at this time this is fx plus f0, and f0 we will show that f0 equal to 0. Okay, so in that case what I am getting, that limit of f of x plus h as h tends to 0 equal to fx. So this means that the function is continuous at x, because x is limit point. Any real number is a limit point of the set of real numbers. So limit of h tends to 0 f of x plus h is equal to fx will be will imply that the function is continuous at x.
Therefore, f is continuous at x, that is, f is continuous over entire R. Fine. Next step is to show f0 is equal to 0. How do we show this? This is very easy. F0 is equals to f of 0 plus 0. I have just written 0 equal to 0 plus 0. Okay, I have not used any property of f yet. 0 equal to 0 plus 0. Now, if I apply the property of f of 0 plus 0 will break into f0 plus f0. Now we have f0 equal to f0 plus f0. You cancel one f0 from both sides, then you are left with f0 equal to 0. So this one finally justifies the continuity of the function at the point x, any real number point x. This information was needed before this step. So next up, so again for every real value x in R, f0 is 0. So 0 I am writing as x plus minus x. So f of x plus minus x, by using the additivity formula again, fx plus f of minus x. So then therefore you take fx to this side, you get f of minus x is equals to minus of fx. Okay, so this is an odd function. F of minus x is equals to minus of fx. This is an odd function. Up to here we are sort of building our premise that it is continuous, the value of the function at 0 is 0, and it is an odd function, that is f of minus x equals to minus of fx. So we built our premise over here. What is left is we are going to show the rest of the thing, fx equals to kx, in the following way, that x is a positive integer. We will show that fx equals to kx. Next, x will be an integer. We will show fx equals to same kx for the same constant k. Next, we will assume x is a rational number. Then fx will be k times x again. Then we will assume x is any real number, and then we will show that fx equals to kx holds for that thing as well. We will be using the result that it is true for positive integer in the case of negative integers. We will be using the case of integers while we will be proving the case for rational numbers. We will be using the result for rational numbers while we will be proving for irrational numbers. Okay, so this is so nicely neat. Okay, now if x is a positive integer, then if x is, now here x is a positive integer like 10, 11, like this. So you can write x as 1 plus 1 plus 1 plus this way x times. Okay, and this one by additivity property of f breaks into f1 plus f1 plus f1 x many times, and that is x times f1, and that is your k times x. What is your k? K is f at 1. So for positive integers we have proved that this is the case. For negative integer, if x is a negative integer, then minus x is a positive integer, right? If x is minus 3, then minus x is equal to 3. Therefore f of x is f at minus 1 plus minus 1 plus minus 1 up to minus x times. Okay, understand this a bit critically. Suppose x is minus 3, then minus 3 will be minus 1 plus minus 1 plus minus 1. So that is how many times? 3 times, and that 3 is minus of minus 3. So therefore by additivity again, it will break f of minus 1 plus f of minus 1 plus f of minus 1. Here it will go minus x many times. Okay, now f of minus 1, using this formula, f of minus 1 is minus of f1. So therefore minus x times f of minus 1 is minus x, same minus of f1. So minus minus cancel, so this is x times f1. So see, my constant is same, so this is k times x. So for any positive integer it is k times x, for any negative integer it is k times x, at 0 it is 0. So for any integer fx equal to k times x, this is proved for the constant k, which is f at 1. Next we will prove for rational points. So let x be a rational point of the form p over q, where p is an integer, q is a natural number. Then qx equal to p, no doubt about that, and hence k times p understand this thing, k times p is an integer. So k times p will, if p will be k times p, because we have proved that for any integer the functional value at any integer point is k times that integer. So f at p is k times p. Therefore, now this p is qx by our this thing, this relation x equals to p over q. So qx equal to p. So p is qx. Now q is a natural number. Qx is x plus x plus x plus this way q times. Okay, q is a natural number. So q times makes sense. So f of x plus x plus x plus this way q times. Apply additivity again. So this is fx plus fx plus fx. This way it is goes q times. So this is q times fx. Finally, you see, so fx is equals to k times p over q. So fx equals to k times p over q. That is p over q is your x. So kx. Now what is remaining is for irrational points. So finally, let x be any irrational point. Choose a sequence xn of rational numbers converging to x. Right? Since f is continuous at x, by sequential criteria, the sequence functional sequence fxn must converge to the point fx. So whatever will be the value of limit of f of xn, that should be the value of f of x, since we have shown that f is continuous everywhere. So as xn's are all rational, f of xn is k times xn, no doubt about that, and k times xn tends to kx, xn tends to x, that is our hypothesis. So kxn tends to kx. Okay, so the functional value fx must be kx. So fx is equal to kx, and that holds for every x in R.